Just some reminders. I kept mentioning that the last lab is the Rlc Lab, but actually it isn't. It's the last lab that you're doing is turning in your lab kits, and that is due on May 25th. Okay, so you have instructions on how to turn in your lab kits. I'm not sure what you're, Makala, what you're referring to in the chat. Okay. Oh, okay, that's fine. Turn them in turning your lab kit by the 25th. There's going to be a container outside of Sewell in which you can drop off your lab kit. Okay. Once Tyler records the lab kit, then I will give you the credit for the lab kit. So this is kind of late because I only have a couple days after that to record grades. Okay, so I kind of need them by that date. Okay, because I'm also going to be grading your Rlc Lab, which takes forever to grade. Yeah, there's just containers sitting outside of Sewell. So hopefully nobody takes anything. I mean, people have been pretty good about it. So because we have to keep the place kind of closed, we can't have you come into the building, so we just leave a drop off. Okay, Chase? The Rlc Lab is due May 22nd, and people, over the last couple of days were kind of complaining about all the work they had to do and stuff like that, and I understand that, but I also need to get stuff graded, so this is a firm deadline on this lab. This is the longest lab you will do this semester. Okay, the previous lab that you did, or the one that's due tonight, which I give you an extra day, that's a fairly short lab. I mean, very short lab compared to this. Okay, so I need that turned in by the 22nd. Yes, Vincent, regarding the lab kits, you should write your name on the lab kit, because that way I'll know who turned it in, and Tyler will know who turned it in, so that way we can record it. So we do need to know your name when you turn it in, because otherwise we have no way of knowing, of recording it being turned in. Because again, this is a lab grade, so you turn it in, it's a 20 out of 20. Okay. These are the deadlines for the last two homework assignments. Again, no extensions. I'm not going to take any extensions on anything anymore now, because we're getting towards the end of the semester. You guys got to get things done. Okay, now granted, and I should be honest about these two, and I think people keep forgetting, you can always click the extension button on WebAssign, okay, to give yourself an extension on the homework. Okay, and I mentioned, that was something I mentioned at the beginning of the semester. Okay. So today what I want to do is talk about chapter 33. And I think I've sent all the remaining notes for the semester. I think I've sent you guys the 33 and 34 notes. And so today and Thursday I will cover chapter 33. In the lab on Thursday, I'm going to go through some of the heavy duty analysis for the Ilrc Lab. Okay, and I will probably solve the differential equation like I did for the transient lab. Okay, and I apologize, although some people were happy that we didn't have to do part 3 for the transient lab. We didn't give you the smaller capacitors, so that the smaller capacitors were not included in the lab kit, so there was no way you'd be able to see the Rlc transient, the underdamped circuit. There was no way you could see it unless you had your own capacitors. Okay, so we had to skip that. So what we want to do today is talk about AC current. Okay, so our focus on AC current. We're going to talk about phasors and AC current analysis. And we're going to do it in a much more physical way than instead of applying Kirchhoff's laws and solving a second order differential equation, because sometimes you get lost. The mathematics kind of clutters the physics. Okay, so I'm going to introduce a topic that if you had 215, you might have seen it. It's a concept called phasors. Okay. So let's talk briefly about what is AC current. What is alternating current as opposed to direct current? Okay, so you didn't cover phasors in 215. Okay, depends on the instructor. I tend to do it because it helps me to explain some of the topics better. So DC current is basically unidirectional flow of charge. Doesn't mean that the current's constant. It just means that the current is in a fixed direction. So if you plot I versus time, and the current does this, for example, just an example. This is called DC current. Even though the current's not constant, it's in the same direction. AC current's different. AC current means alternating current. It means that it's bidirectional flow of charge. Okay, and the primary problem in this chapter is given an AC voltage along with the frequency and values of your components, find the current in the circuit. That's what we're going to be learning here. Okay. So I need to say a couple things about notation for this chapter. We're going to use small letters for instantaneous values, and I'm going to try as hard as possible to write a script V for instantaneous value as opposed to a regular V. I mean a script, but cursive V for instantaneous value, because it's hard to differentiate sometimes between these two. So I'll write this. So these two to me are going to be the same. Okay. I'll try as much as possible, because otherwise it's hard to tell the difference between the capital letter and the small letter. Okay. So small letters are going to represent instantaneous values of current and voltage. Capital letters with the subscript M are going to be representing maximum values or peak values. And then there's a third one. Capital letters with the subscript RMS are going to represent root mean square. And I'll talk about what root mean square means. Okay. So, and we're going to really focus on the capital letters, quantities involving the capital letters. We're going to be looking at really not the time-dependent part of the voltage, but the time-independent part of the voltage. So one other question is, if I have an AC power supply, and by the way, the AC power supply we're going to be talking about is a current or a voltage that looks like this. In our chapter,
Professor?
yes.
As what our multimeter measures?
Oh, we're going to get to that. I'll talk about what the multimeter measures.
It is not RMS?
It is RMS. But
Okay.
yeah. The multimeter measures RMS, but I'm going to get to that. So all power supplies in this chapter are going to be sinusoidal. Same as what comes out of your outlet. I can use sine or cosine here, but I'm going to use the convention I'm going to use is cosine. Sine is just this with a phase factor of 90 degrees. Okay? So I'm going to use this in all the engineering books for their power supply, write their voltage like this. Our textbook is different. I don't know why, but they use V sub m sine of omega t. They want to do something different, I guess, but it's actually not the best way to represent the voltage. And I might say something about that later. Okay. So here's your power supply voltage, and and this is the symbol for our AC power supply. You hook it up to a resistor, and if you make a measurement and you look at the current as a function of time, you will see that Ohm's law is obeyed for the resistor. The only thing is that V and I change with time. So little I is V over R, which would be V sub m cosine omega t over R. And let me explain it, and I didn't get to explain this. Omega is 2 pi times the frequency. Okay? This is the number of cycles per second. So if I were able to plot this function, the frequency is 1 over this time period. This is called a period, and that's 1 over the frequency. Okay, and you folks already know how the sine function works, even when you write the sine and cosine function like that. Are we okay with that? And if you were to plot the voltage and the current on the graph, you would see that their peaks occur at the same time, and their minima occurs at the same time, and their zeros occur at the same time. Moreover, the voltage and the current are in phase with each other.
Okay. Wait, real quick, what does that say on the graph? T equals 1 over F?
The T is the period, right? The time it takes to complete one cycle for this function.
Oh, okay.
And so this is the number of seconds per cycle. Frequency is the number of cycles per second. Okay. Yeah, you're right. So I didn't change the picture. So I took the picture from somebody else. But I'm going to be using the cosine function like the book. I actually took this picture from, I think, an old textbook, an old version of our textbook. Either that or from a faculty member who's not here anymore. And they use sine. But of course, it doesn't matter because all I got to do is shift this 90 degrees, and really it's not a big deal. Okay, whether I use a sine or a cosine doesn't matter. Whether I use a sine or a cosine is going to depend what I set V to at t equals 0. So it really doesn't make a difference. So we can write the current like this. And this is the amplitude of the current, just like this is the amplitude of the voltage. And so the amplitude is basically this value, which I'll use in a different color. Sorry, I'm writing small. That's V sub m. Okay? And if I were to plot I sub m as a function of time, or I as a function of time, sorry. I know I'm plotting sine functions, sorry about that. It's I sub m. Okay, if you don't like me plotting the sine function, I'll just move my axis over to there. Okay? That's all I have to do, right? All I have to do is shift the axis over. And I just got to do this. But it doesn't change the shape of the function though, right? I haven't changed the shape of the function. Now, when you measure V or I with the multimeter, you notice that the value that you read is constant. That's because the multimeter cannot, well, you won't be able to tell what the voltage is if the voltage changes very quickly. If you were to measure the voltage from the wall socket, it varies at around 60 times a second. And so if you had a multimeter where the value changed 60 times a second, you wouldn't be able to see it. I think the fastest your eyes can tell is like 20 times a second, something like that. I forget the value is. Okay. Just 1 second. I keep hearing a lot of background noise. Okay, that helps. So, in order to understand what the multimeter measures, we got to look at the power. Okay? In order to understand what the multimeter measures, we have to look at the power, the energy dissipated by this resistor. And we want to look at some sort of I effective or V effective. So let's write the expression. If we know this and we know this, let's write the expression for the total power. Okay?
Does that V under the AC power that represents the voltage of the power supply?
This one?
No, the other one.
This V?
I guess the instantaneous voltage.
That's
of
the
power
instantaneous
supply?
voltage. That's the maximum. That's the amplitude.
Is that from the power supply or across the resistor?
Well, in this particular case, they're the same, right? Because the voltage across the power supply has to be equal to the voltage across the resistor, right? Otherwise, we're not obeying Kirchhoff's voltage law. Isn't that true?
Yeah, but does that represent the voltage, like the potential difference across the whole circuit, like at a moment in time?
I'm not sure what do you mean by the whole circuit. If you do the whole circuit, it's zero, right?
Yeah, but I mean like the basically just does that represent the power supply voltage?
Yes.
Okay.
So let's look at power. And what we want to determine is some sort of an effective voltage or some sort of effective current for our system. And that's going to be indicative of how the multimeter works. So we're going to get to that. So our power can be written as I squared R. Of course, you can write it as V squared over R. I'm gonna write it like this. My notes are, there's a mistake in my notes. It should look like that, I guess. No, actually our notes are fine. Okay. And what I want to do is write it in terms of some sort of I effective times R, but we'll get to that. What I want to do is write the following. I want to write P average. I want to look at the average power like this. What is the effective current over a cycle? Or what is the average power over a cycle? I want to write the following. Oops, I forgot the R. Suppose I take the average value of this. What's going to happen to my R's? Okay. How do I find the average of this function? From calculus. What we're really looking at is, let's calculate the average power over a cycle and define some sort of effective current. Does that help, Chase? Does that help with your question? We're just trying to define some sort of effective current. So basically, now this I is constant, so I can actually pull this thing out because this is voltage. This is the amplitude of the voltage over the resistance. So I can take this guy and put it over here. And so my job is to figure out the average of the cosine squared omega t. I need to find out what that turns out to be. That represents the average of a function that you have learned how to do in Calc 2. Okay? So without doing formal calculus, let's do it a little bit different way. Okay? What's the average of cosine over a period? Anybody? What's the average of a cosine function? Oops, 1 second. Isn't it 0? Yeah, the average of a cosine function is 0. But the average of cosine squared is not 0. So we want to figure out what the average of cosine squared is. And I'm going to do this without actually doing the integral. Okay? So let's take a look at cosine squared. Can we rewrite cosine squared? Of course, we can use a trig identity. Cosine squared is 1/2 times 1 plus cosine 2 theta. What's the average of this? Isn't that 0? The average of cosine 2 theta is 0. Okay, if you don't remember it, just integrate it over a period and you'll see that it's 0. What's the average of a half over a long period of time? In other words, if you have a function that looks like that, what's the average of that? It's just the value, it's the function itself. So if I average this function, the average is going to be a half. Okay? And if you don't like the way I did it, you can always do this integration and do it the brute force method. And you're free to do that. But what you'll get is I effective squared is equal to I sub m squared times a half. And so I effective is I sub m over the square root of 2. And we're going to call this I effective the root mean square current. Your multimeter measures root mean square values. And it does it different ways. It actually doesn't do it directly. Like one of the ways it does it, one of the ways it can do it is by taking the voltage, converting it to a DC, and measure how much power some sort of resistor in your multimeter uses up, and then converts that to a voltage. That's one of the ways it's done. Okay, it doesn't necessarily take a true RMS average. Okay, so there's different ways. There's multiple ways a multimeter can get this value, and there's issues associated with it. And so when you look at multimeters, depending on how much you pay, the frequency range of the multimeters when they measure AC current is limited. Okay, it just depends on how good your multimeter is. But what they do measure is an RMS current, and they measure an RMS voltage. I could have done the same thing with voltage, because I could have written this as V squared over R and done the same thing and find a V effective, and you would see that VRMS is V sub m over the square root of 2. Okay, so the RMS is the square root of the average squared value. For AC. So what's the VRMS? Well, we do the same thing with VRMS. VRMS is 0.707 V max. So if you were to take your multimeter, okay, if you were to take this multimeter and stick the probes into the outlet, I guess I probably don't recommend that you do that, since you don't have somebody like me around to help you do it, so don't do it. But if you were to stick that into the outlet, it would read 120. That 120 is an RMS. V max is 120 times the square root of 2, which is around 170. So the peak voltage out of your outlet is about 170 volts. So if you plot voltage as a function of time from your outlet, I'll do one cycle. This is 1/60th of a second. This is about 170 volts. And this is minus 170. So peak to peak is 340 volts, but the RMS value is 120. Okay, that comes out of most of your outlets. I shouldn't say all of them, but most of them, because you do have services in your home that are 240 volts, like for your air conditioner, your oven, etc. Devices that require a lot of current or a lot of power, they'll have 240. Your dryer, if you have an electric dryer, it'll run at 240. Okay. So the RMS value basically is the maximum value divided by the square root of 2 for sinusoidal alternating current. Okay, is everybody clear on that? So what about if I don't have a sinusoidal current? What if I have a triangle one? What is the RMS voltage? What if I have something that's repetitive like that? I want to know the RMS voltage. So let me draw this on the graph. Suppose I have some weird power supply. That does this strange thing. Okay, and we'll call this V sub m here. How do I figure out the RMS value?
Can it be the same as the maximum value?
Can the RMS be the same as the maximum value?
Yeah.
Only if it's constant.
Yeah.
Okay, if it's constant, yeah, that's true. But if it's not constant, that's not the case. So how do I do this? Well, first of all, I need to know the equation of this line. What is the equation of that line? Let's call this, let's point the period. How do I write the equation of this line? I want to write the expression for V.
Find the slope.
The slope, what's the slope of that?
V sub m over t.
Times the time, right? Mm-hmm. The y-intercept is 0. So that's V. So I want to take, remember, it's the average, it's the square root of the average of the square of the function. So what's V squared? Well, it's V sub m squared over t squared, big T squared, and little t squared. So it's V sub m squared over big T squared times little t squared. Little t is the elapsed time, big T is the period. Now I got to take the average of this. The average of a function is 1 over the interval times the integral over that time interval of the function. And again, if you don't remember this, review your calculus, because I know you did this in calculus. What does the integral give you? What's the integral of t? What's the integral of t squared?
Cube over 3.
T cubed over 3, right? What does this come out to be? And so, I'm running out of space. VRMS in this case is V sub m over the square root of 3. Okay, it's the average of the square root of the average of the square of the function. That's RMS. Okay. So that's it. So let me go ahead.
Does the number 3 have to do something with it being a triangle shape?
Yeah. It has to do with the shape of it, right?
Mhm.
If I had a different shape, it'd be a different value.
No, like it was similar to the number of sides a triangle has.
Oh, okay. That I don't know. I mean, I'd have to do a sawtooth. I mean, the other option is to do something like this. And see what that gives.
Mm-hmm.
Okay, I'd have to compare to that. I don't know off the top of my head. First of all, I want to ask this question. Why do we use AC current in our homes as opposed to DC?
Because with DC, if one component goes out, then the rest also go out.
That you're talking about series, not you're talking about connecting
Oh, wait,
things
my
in
bad.
series.
Is it a lot safer to have it have AC current than DC current?
Actually, AC is more dangerous. In fact, I don't know. I put a video on Canvas. This guy called Electroboom. He talked about AC versus DC, and Edison developed the electric chair just to show how dangerous AC current is. Our body has a capacitance, and capacitors block DC current, but they don't block AC currents very well. I'm sorry, go ahead.
I was just saying that I think I heard it somewhere that they use AC. It has something to do with the use in transformers. I don't know, something like that.
Yeah, you can. You can use transformers. First of all, they work with transformers. DC don't, right?
Mm-hmm.
Yeah, and Kai, you mentioned one thing, and here's the thing: you're also on the right track too. So both of you are on the right track. Number one, DC power supplies don't work with transformers. Okay, that's usually a question I had to ask on a test. AC power supplies do because the current varies. But then the other question you're referring to, Kai, is this. The average power for AC is 1/2 I max squared times R. For DC, it's I max squared times R for a given I. So you lose half the power with AC, right? Because this is constant. You lose half the power with AC as opposed to DC. Then why don't I use this? Because then I would lose 1/3 of power. Why can't I use that weird function? Right? Why can't I use this function? A triangle function. Because I lose less power. Because over a cycle I would lose 1/3 instead of 1/2.
I don't know. It somehow looks abrupt change compared to the sinusoidal that we have.
Yeah, and this is a hard question. It is very difficult to generate this. This requires you to use a linear combination of sines and cosines. Okay, whereas a sinusoidal one, all you got to do is rotate a coil in a magnetic field and you're done, you got it. Okay, but to generate this is much more difficult because you need linear combinations of sines and cosines in multiples of omega times t. Okay, that's why we don't use this. This is much more difficult. By the way, Europe uses 50 hertz, we use 60 hertz. Notice the frequency doesn't factor into any of this. All right? Whether you use 50 hertz or 60 hertz doesn't affect this number. Okay.
Why do we have different frequency then?
I have no idea. People don't like having the same standard. One of the problems, though, is if you want to switch, yeah, we just want to be different. But if you want to switch from all the machines to a metric system, that's going to be very expensive. Right, if you're using a machine to build a milling machine, I don't know how many folks, you guys haven't had a chance to really work in the engineering lab because we have a lathe and milling machine and all that. They're all in inches, but it costs a lot of money to change that from inches to meters or millimeters. Okay, it's very expensive. That's one of the reasons why we haven't changed. It just costs too much. So our standard outlet, like I said before, is 120, and Vmax is about 170. Okay. All right. So we've done the resistor in series with the power supply. What if we want to do the capacitor in series with the power supply? What if we want to do the the inductor in series with the power supply? What if we want to do combinations of them in series with the power supply? Then what? Well, I would have to solve a differential equation, a second order differential equation, after I apply Kirchhoff's laws. Again, the mathematics can hide some of the physics. And so I'm going to do something a little bit different in studying AC circuits and analyzing AC circuit. I'm going to introduce the concept of the phasor. And the idea of the phasor comes from representing a number, a complex number in the complex plane. That's where it comes from. That's where the idea of this phasor comes from. We don't have to know all those details, okay? But for us, a phasor is a vector that's placed in a standard XY coordinate system. It is used to represent a physical property that changes periodically. By the way, what I'm about to say right now, the idea of the phasors, make sure you're clear about this, only works for sinusoidal currents. Okay? It only works for sinusoidal currents. It does not work for other types of signal generators. It does not work for a square function, triangle function, only sinusoidal. Okay? And this whole chapter is on analyzing sinusoidal systems. Now, the length of the vector represents the maximum value of the property, and the vector rotates counterclockwise with the same frequency that the property represents. This is different from the textbook. And I don't know why the textbook chooses this method. It's very annoying that they do it this way. But we're going to do what all the engineers use. The instantaneous value of the property is the projection of the vector onto the x-axis. I'm going to draw a picture in a second. You can draw more than one phasor at a time. And the result is a phasor diagram. So let me draw a picture representing a phasor. This has nothing to do with Star Trek. And I can draw it for voltage or for current. It doesn't matter. So if I draw a phasor that looks like this, this is V sub n, this is the length of it. The projection onto this axis is the instantaneous value. Let's not worry about the projection onto the y-axis if you're thinking about that. I mean, it does have a meaning, but not for us, okay? Let's ignore that part. That clear so far? So this thing rotates constantly. So if we're analyzing what's coming out of our walls, this thing rotates 60 times a second. Okay? And we're looking at it at an instant in time. Is this a Calc 3 concept, the phasor diagram?
I'm not familiar with the phasor diagram, but we did the projections in Calc 3.
Oh, okay. The dot product. Right, if you project it onto the x-axis, that's a dot product. So this is the instantaneous value. Anything along the x-axis is the instantaneous value. Okay? Are we clear so far?
Mm-hmm.
So here's a graph showing you, maybe let me make the screen a little bit bigger so you can see it. This shows you the resistor circuit. It shows you the phasor diagram for the voltage and the current, and it also shows you the projection of the values onto the x-axis. Sorry for the yellow letters. They're hard to see. And you're looking at, you're basically looking at it at one instant in the cycle on the graph. Okay? The length of the vector stays the same, just the projection changes, and it's the projection that you're looking at on the graphs. And it shows you that V and I are in phase, because when I draw V and I on the phasor diagram, V and I overlap each other. But what about an inductor? What if we do an inductor? Let's say the power supply voltage is V sub m cosine theta. Of course, the voltage across the inductor is going to be V sub m cosine theta because of Kirchhoff's voltage law. Can we solve for the current from that? Of course we can. Okay. How do we solve for the current? We're going to do the inductor. How do we solve for the current? What am I assuming about the inductor?
No resistance.
No resistance, you're right. So we're going to write it as V sub m cosine omega t. I'm going to bring the dt up here. And guess what I'm going to do next?
Integrate.
Integrate. So let me divide both sides by L. I want to integrate from 0 to some final t. And that's going to give me I. What am I going to get when I integrate this? Does that look okay? Can I write it this way too? Isn't that the same thing?
Mm-hmm.
So doesn't it say that the current lags behind the voltage by pi over 2? Also, I can do the following. We do this so that we make it look like Ohm's law. So we let omega times L equal X sub L. Because if you look at the units of this has units of ohms. And so we write I equals V sub M over X sub L cosine omega t minus pi over 2. So the current lags behind the voltage by 90 degrees. And X sub L is called the inductive reactance. We write it like this because we want to make it look like Ohm's law, like a voltage over resistance. So that's the inductive reactance. Here's a phasor diagram for the inductor and for the inductor voltage and the current. Let me blow the picture up for you guys. There's a picture. There's V ahead of the current by 90 degrees. It also shows the projection of V onto the x-axis and the projection of I onto the x-axis. It might say, okay, great, so what? Why is that interesting? It looks like obvious stuff, but why is it important to draw it on that graph? Right? Chase, yeah, Chase, you're right. This is so impedance includes the resistance, Chase. So the next problem I will do will include both the inductor and the resistor. So it turns out, and I'm going to try, I was going to try to avoid this, but in reality, when you solve this in an engineering course, when you solve in an engineering course, instead of writing the power supply voltage like this, you write it as a complex exponential. And the real part of the solution is what you want. Okay? And the imaginary part involves the X sub L. The real part involves the R's. It really works out beautifully when you're using complex notation. And it's much faster than what we're doing here, especially when you're doing complicated circuits. Okay? We don't have time to do those though. Notice that V equals V max when di dt is a maximum, and V equals 0 when di dt is 0. Okay? The slope of the tangent line. Di dt is the slope of the tangent line. So we're going to denote X sub L as our inductive reactance. And this is a measure of the opposition to a changing current. Why does X sub L increase with omega? Why does X sub L increase with frequency? Why is that? Why does X sub L increase with frequency?
Isn't the rate of change much higher than the opposition would be higher?
That's right. d phi dt is bigger, right? D phi dt is bigger when frequency is higher. And of course, that means that you have greater opposition to a changing current. Now let's make life a little bit more complicated. Life isn't simple, right? We're going to throw in a resistor. And you say, okay, well, what do I do now? Where do I go from here? Because I have to solve Kirchhoff's voltage law. So let's write the power supply as this. I'm just going to draw a phasor diagram. Okay? And I'm going to draw it in as simple way as possible. First of all, let's use our knowledge. The inductor and the resistor are in series. What do we know about current? The current through both of them.
Same.
They got to be the same, right? So the current through both of them is going to be the same. So I'm going to draw the current, the phasor that represents the current. I'm going to make life easy for myself. I'm going to draw the current on the horizontal axis because it's going to make everything easy for me to draw. Okay? So I know that the current through the resistor and the inductor are the same because they're in series. So I'm using my knowledge. So I'm going to write I sub m here. Then I know that the voltage across the resistor is in phase with the current. Isn't that true? Because that we showed that already. Right? So I'm going to draw the voltage across the resistor. I'm going to use V sub R, but this is the maximum voltage. Okay? Anybody object to what I just did? Because isn't the voltage across the resistor I times R? The answer is yes. And that means that this vector is just scaled version of this one. Now, what did we just say about the voltage across the inductor? How far ahead is the voltage across the inductor as opposed to the current? Didn't we say the current lags the voltage by 90 degrees? So then all I got to do then is say, okay, let me draw the voltage across the inductor. I have two vectors that are perpendicular to each other. So let me draw V sub L over here. This is the power supply voltage. And now the phase shift between the voltage and the current, I'll use the Greek letter phi. I'm done. And in fact, this is going to be so easy for you guys. Watch this. And again, this only works for trig function, for sinusoidally varying power supplies. Using the Pythagorean Theorem, V sub m is equal to the square root of V sub r squared plus V sub l squared, which is equal to the square root of I sub m times r squared plus I sub m times x sub l squared. I can solve this for I. This is, the denominator is called impedance. And from trig here, you can see that cosine of phi is equal to V sub r over V sub m. Sine of phi that's it. Everything's summarized in that graph. I mean, that slide. That's all I had to do. I didn't have to solve a second order differential equation. I just used physical arguments in the Phasor diagram. Question on this? This is a very powerful technique.
Professor?
Yeah.
How did we know that the maximum current was flowing through the resistor? Are we like at the steady state?
Well, first of all, we're looking at an instant in time, right?
Mm-hmm.
And we know that the voltage, the current through here and the current through here have to be the same.
Mm-hmm. Yeah.
So it doesn't matter how I draw that, right? I mean, I could have drawn the picture with I sub m downward, but then I'd have to draw everything relative to that. I sub m is my standard that I use because I know that the voltage across the resistor is in phase with the current through the resistor. So I use that as my standard to start from. Okay, let's see. Is there a conceptual way to understand why the current lags by 90 degrees? Well, you mean for the inductor, isn't the voltage across the inductor di dt? And isn't the derivative of a cosine a sine? Aren't they 90 degrees apart? Right, that's what we established with the Phasor diagram, right? So just use that idea. That's all you need to remember. You do have to remember that 90-degree phase shift is because of the fact that the voltage across the inductor is di dt, and the derivative of cosine gives you a sine.
Wait, so what is that? What is the value of z? Is that just a way to represent square root of r squared plus x squared?
The way to represent this is z. And so this is called the impedance, because Chase asked a little while ago, is that the impedance? The impedance is the combination of these two. So it's the resistance and the reactance. You combine them together, you get something called the impedance. Okay. So then the current lags the voltage by phi. So the current then is going to be that's going to be what the current looks like. Then the voltage across the resistor is going to be this times R. The voltage across the inductor is going to be L times the derivative of this with respect to time. And I have all of that in the slide. So what you need to do is to work through that slide. So you can figure that out. You want to work through everything in that slide, okay? Especially the last equation that you see there. So for you, this should be a homework problem for tonight, is to derive everything in that slide. Because that's the only way you're going to understand it. You got to work through it yourself. If you sit there and try to memorize it, you're not going to understand this. Okay, you got to work through it yourself. Now the other thing too is tangent, the tangent function. What's tangent of phi? Well, it's v sub L or v sub R. It's that. And we can write the voltage across the inductor and the voltage across the resistor very easily. The voltage across the inductor I take the time derivative of this, Okay, I'm going to get the following. Remember, this is omega times L. And this is x sub L. I'm going to write it like this. And the amplitude is this. But this is x sub L, right? Actually, I'll leave it like this. In fact, I'll write it this way too.
I think your camera just froze.
Okay, thank you. Let me fix that. Where I have to turn it off and on. Okay, thank you. So this is V sub L. This is this guy. This is the amplitude. As omega goes to infinity, well, as omega goes to 0, what is V sub L? It's 0, right? The numerator is 0. If I make this 0, if the frequency is 0, this whole thing is 0. If I make this go to infinity, then this whole thing goes to 1. And so we say that this thing passes high frequencies. I don't know if you've heard the term high pass filter, low pass filter. I don't know if anybody has taken mechatronics classes. Okay, these are the basis for building filter circuits. Okay.
So as omega goes to infinity, V sub L goes to V sub M, right?
Yeah, V sub M. I'm thinking of the ratio V sub L over V sub M.
Okay.
Yeah, but yeah, you're right. V sub L approaches V sub M. I always think, I always look at it like this. Actually, engineers, what they do is look at this ratio. And so now as omega goes to infinity, this goes to 1. Okay, but yeah, electrical engineers look at this ratio. And they make a plot of this ratio as a function of omega. They call it a Bode plot. And this is the basis of forming simple filter circuits that you learn either in mechatronics courses or in the Engineering 17 courses. But we just don't have time to talk about the basics of filter circuits. So let's do the capacitor now. What if we replace this with a capacitor? No resistor, just a capacitor. Capacitors actually are kind of nice because they act more like a pure capacitor. Inductors are not pure because they all have a resistance, but capacitors are not like that. You have less issues, especially like at extreme frequencies. So the power supply voltage is this. And so the voltage across the capacitor is that. The Q, what's Q across the capacitor? So what's I then?
You're right there before us answering the questions.
I'm sorry?
I'm saying you write the answer before you let us answer the question.
Oh, I'm sorry. I didn't hear. I didn't hear the. I probably didn't hear the answer.
Is
Sorry
that a
about that.
negative omega?
Yeah, because when you take the derivative of cosine, don't you get the minus sign out there? Right? Isn't the derivative of cosine minus the sign?
Yeah.
Okay. So this is the current then. I is omega c v sub m sine omega t. Sorry. This is the same as omega c v sub m cosine omega t plus pi over 2. And so now we're going to make this look like Ohm's law, I'm going to define omega c as 1 over x sub c. So then I is v sub m over x sub c and this is called the capacitive reactance. Okay. What do you see? You see that the current leads the voltage by 90 degrees. Okay. The current leads the voltage by 90 degrees in this particular case. So the phasor diagram looks like this. This is just an example at an arbitrary angle, but I put I sub c 90 degrees ahead of v sub c. And there's a graph of I and v as a function of time. And again, the projection onto the x-axis is what you see on the graph. Those vectors, capital V sub c and I sub c, are the amplitudes of the function that's graphed on the left. So for a sinusoidal applied voltage, I sub c always leads V sub c by 90 degrees. And so I'm going to leave it to you. You can ask me during office hours if you want help on this. Can you draw a phasor diagram for RC circuit? Okay. So the capacitive reactance then we define as x sub c is 1 over omega c. So let me write that down. And again, remember, omega is 2 pi times the frequency of the signal. And again, the units in x sub c is the same as the units on x sub l. They're units of ohms. And I think what I'll do in lab on Thursday is just show it to you. That they do indeed have units of ohms. As omega approaches 0, so does I. Which means that capacitors tend to block DC current. As omega goes to infinity, then x sub c goes to 0. Capacitors pass high frequencies. So let's do one more. This is the highlight of the chapter. It's this circuit. It's a series LRC circuit. Given power supply voltage L, R, and C, this is your lab. How do we determine everything? And guess what I'm going to do? I'm going to draw a Phasor diagram. And it's really straightforward. Again, we're going to use the ideas that I just talked about. So what I'm doing here is not new. I'm just building on what we know so far.
Professor?
Yes.
What was the meaning of capacitive reactance?
Oh, the meaning of it. It's in opposition to the charging of the capacitor. The higher the frequency, the current passes through, right? I mean, that's how we say it. The lower the frequency, then the current gets blocked, but which means, so it basically blocks the current for a large X sub C.
Yeah, I could get it for the inductor, like the opposition part, but I could not really see the opposition by a capacitor.
Well, it basically it blocks the current. The higher X sub C is, the more it blocks the current. It reduces the current.
Mm-hmm.
The lower X sub C is, the more it acts like a wire. So basically, you can say it's an opposition to current.
Mm-hmm.
Okay. Let's do the Rlc circuit. Some people say LRC, some people say RLC, doesn't matter. And I'm just going to draw a Phasor diagram. And again, what do I know? They're in series. What do I know if they're in series? What do I know about the currents if they're in series? Yeah, the current is the same. Sorry, I didn't see that. The current is the same in each element. And I know that the voltage across the resistor is in phase with the current. So let me draw the current through the resistor. I'm always going to start on the horizontal axis because I like it. You don't have to do that, okay? But I mean, you can start at a weird angle, but then you got to draw everything. You know, it's a little bit more confusing. I always start here. Let me draw in red the voltage across the resistor. And I know the current through the resistor, the current through the inductor, and the current through the capacitor, they're the same. What do we say about the voltage across the inductor? It was 90 degrees ahead of the current. I'm just arbitrarily making it longer. And let's draw the voltage across the capacitor. The capacitor, the current leads the voltage by 90 degrees. So then the capacitor voltage has got to be somewhere down here. So these two actually subtract from each other. So I'm going to put the difference over here. And then my power supply voltage, I'm sorry, let me see if I have another color. I don't. I guess I'll use black. Is V sub m. And so V sub m squared is equal to V sub r squared plus V sub l minus, oops, We can write it this way. I sub m times r squared plus I times x sub l minus I times x sub c squared. I can pull out the I. And so I get I sub m squared and so V sub m and I and of course, Z then ends up being and this is the impedance. This triangle tells you a lot of stuff because we can see that tangent of phi cosine of phi, hold on, one too many steps. And sine of phi
Professor,
yeah.
on the top, shouldn't that be a Z on the
Oh yeah,
denominator?
there should be a Z, thank you. Because I did that here. Okay, thank you. This is called the impedance triangle. That triangle tells you everything you need to know. Okay. Questions on this? So what we know, IAC has the same amplitude and phase at all points in the circuit, and we already said that. And the voltage across each element have the same phase relationship to the current as determined by the isolated elements. And so then we can write I I drew two of them in this figure, one that's rotated, so you can see where the sine omega and cosine omega term. So if you take V sub m or V sub r and you project it onto the x-axis, you can see where the cosine term comes in. If you look at the phasor diagram on the right, you can see where the cosine term comes in across V sub r. And then you can see where the sine term comes in on the other elements. Okay. So your lab is studying this circuit. And so your impedance, and I'll go through this real quick. This is a generalized form of Ohm's law when you write it in terms of the impedance. Okay, V sub m is I sub m times Z. It's like writing it in a generalized form of Ohm's law. So in your lab the new lab that you're doing is going to require you measuring V's, calculating X sub L, X sub C about 25 times. You're going to have to actually make a spreadsheet, and then you're going to make 6 plots. You're going to have a data table with at least 150 to 200 data sets of data, and then you're going to make 6 graphs. Or I should say 6 plots because 3 of them go on one graph. So I hope that you read the document I sent you after Thursday's lab. This is the easy version of the lab. If you were on campus, you would actually have to do 9 graphs. Okay. No, it's 8. I forget. I think it's 8. You would plot the phase as a function of time. You would actually have two more columns in the data table. So, but that's the only way to study this circuit and find out everything you need to know about this circuit. Okay. So I'm going to stop here. So next time I'm going to talk about power in the LRC circuit. And I'm going to talk about the transformer. And I'll do a couple of examples, and I have a couple of demos. They're video demos. Okay. And I'll probably do the video demos at the beginning of the class. Questions? No questions? Concerns? I mean, this is why I was concerned about folks wanting the extra day on the lab, because now you're going to have one less day to do the longer lab. Okay. When you start doing the problems, you'll find that these problems aren't that bad at all. And hopefully, when I solve the differential equation in class, some of this will become a little bit more apparent. But what I'm doing here is way easier than solving the DE. I'll do it of course, I'm going to use the method of guessing again on Thursday. Okay. If you guys don't have any questions, I'm going to end it here. All right, have a good rest of your day. And we'll see you either tomorrow night or on Thursday.